Hello, ladies and gentlemen. This is today will be section 7.4, or the beginning of that section, I wanted to say, which is about the integration of rational functions. A rational function is a quotient, that is a fraction where the numerator and the denominator are polynomials. And we're going to learn how to integrate those things today, at least in a special case. So let me pull up the whiteboard. Okay, so 7.4, which is the technique of partial fractions. Okay, so last time on the worksheet, I gave a problem which we kind of got stuck on. It wasn't a complete waste of time though, because it's a segue into this lecture, the integral of dx over x squared minus 5x. The problem was uh, this expression, x squared minus 5x. There's no square root there. And we tried to complete the square. It became an algebraic mess. So I'm going to teach you another technique today, which is very powerful, which deals with expressions like that. So the idea is that the denominator breaks up as a product of linear terms. So it would be x times x minus 5. And the idea is that if you think about adding fractions, then if you have the denominator as a product, you can think of that as probably coming from a sum of two different fractions, where in this case it's some constant over x and another constant over x minus 5. So we have to figure out what those constants are. So that's the idea. Okay, so let's assume that this representation works, that 1 over x times x minus 5 is some number over x plus some number over x minus 5. The number is being called a and b. We have to figure out what a and b actually are. So what we do is we multiply both sides by x times x minus 5 of this equation with the question mark over it. So what are you going to get? You're going to get 1 is equal to a times x minus 5 divided by x, which is the same as a times x minus 5, plus b times x. So now, if you think about what this equation is saying, it's saying that two polynomials are equal. On the left side of the equation, we have the polynomial, which is constant 1, and on the right side of the equation, we have a polynomial which is linear in x, right? So we're going to, the only way two polynomials can be the same is if their coefficients coincide. So one way to solve the problem is to rewrite it as, so what is this? This would be a plus b times x, and then minus 5a. Now, so that's supposed to be equal to 1, and these are both polynomials on both sides of the equation. So that would say that their coefficients must be equal. So that implies the following conditions. It says that, for example, minus 5a must be equal to 1, and a plus b must be equal to 0. To get the a plus b must be 0, because otherwise you would get a contribution of x on the right-hand side. Now, if negative 5a is 1, that tells us what a is. A is minus a fifth, and b is going to be plus 1/5. So we see from this is that 1 over x squared minus 5x can be rewritten as negative 1/5 over x plus 1/5 over x minus 5. And we'll see in a moment that's good. We'll be able to solve this integral in this example in a moment, but I want to tell you another method of actually solving these equations. So this would be like method 1, but there's also method 2. which I think you should know, and it's usually easier to implement. We go back to the equation 1 equals a times x minus 5 plus b times x, and then we stick in some test values of x. And we choose the test values of x so that things vanish on the right side. So we can choose a test value of x equals 0. Now, if x equals 0, the left side doesn't change, but what happens to the right side? It becomes a times minus 5 plus 0. So that tells me that minus 5a is 1, so a equals minus a fifth. And the other test value I can choose is x equals 5. And if I choose x equals 5, I get b times 5 equals 1 with this equation, so b is 1/5. So we get the same answer either way, and there are these two methods, and it's up to you to decide which method to use. I usually find method 2 is easier to implement, and that's why I typically use it. Okay, so let me save the board, and we'll continue with this integral. Okay, so if we look at what we did on the previous whiteboard, we determined the constants. So that tells us the integral of dx over x squared minus 5x is equal to the integral of negative a fifth dx over x plus the integral of 1/5 dx over x minus 5. Okay, and so the first integral, we can bring the minus 1/5 out, and we get dx over x. The integral of that is ln absolute value of x, and I'll put the plus c at the very end. And in the other case, we get 1/5 the integral of dx over x minus 5. So let me point out something that's not hard to show. If you have x minus any constant a, and we take dx over x minus a and integrate it, we're going to get ln absolute value of x minus a plus c. You can see that by taking the derivative, but how did I get this? I can do a u substitution. I can let u equal x minus a, and then du is dx, and then we get what we get, right? So therefore, this second integral that appears is ln absolute value x minus 5, and then we can add the c at the very end, and we've done the integral that was on the worksheet with this, and it was very easy once we implemented this method. Okay. Okay, so let me make some definitions. Definition: a rational function is a function of the form p of x over q of x, where p of x and q of x are both polynomials. And the technique of partial fractions is a technique to integrate rational functions. It's solely designed for that. Now, there are two facts about polynomials that we're going to be using. Two facts. One, every polynomial can be factorized into a product of linear and irreducible quadratic factors. So what I mean by a linear factor, well, I'll just give you an example. 2x plus 3, the highest power of x is 1. And what's an irreducible quadratic factor? That would be something like x squared plus 1. You can't break that up any further as a product of linear factors. as an example of irreducible quadratic. Okay, and the second fact is that we can do long division can be applied to rational functions. So we can apply long division in the case of if necessary. Okay, so I'll explain that as we go along. Okay, so today and only today, we consider the case where the degree, well, let's see, not the degree, but rather the denominator q of x is a product of distinct linear factors. So there are no repetitions in the linear factor. So let me give you some examples of what we're going to talk about today. Okay. Okay, so a non-example of today is the rational function x over x minus 1 times x minus 1. These are not distinct factors, but they're linear, but they're not distinct. So this is no good for today. We'll talk about that case later on. An example of what I mean today is something like x over x minus 1 times x plus 1. Okay, so that's good. That's going to be something we can do today. All right. So let me get started with this, with the method, and I'll show you how this works. Okay, so I think it's best to do this by example. So suppose we have something like x squared plus 1 over x minus 1. There's a single linear factor in the denominator. In the numerator, we have a polynomial x squared plus 1. And in this case, the degree of p of x is actually greater than or equal to the degree of q of x in our case. And if this is the case, we have to do a long division. So what I mean by that is I'm going to divide x minus 1 into x squared plus 1 and see what I get. So x minus 1 goes into x squared minus plus 1 by a factor of x. And if we get x squared minus x, and then you're going to get x plus 1 as what's left over. And x minus 1 goes into x plus 1 by a factor of 1, and then you're going to get x minus 1. If we subtract 1 minus negative 1 is 2. This is the remainder. Okay, so what this actually means is that x squared plus 1 over x minus 1 is equal to, it's equal to x plus 1, that's this x plus 1, plus 2 over x minus 1. And notice now the degree of the numerator in the remaining, in this remainder piece is smaller than the degree of the denominator. And that's a good situation. So in fact, we can even integrate this before I go on. Suppose we wanted to integrate now x squared plus 1 over x minus 1 dx. Well, that would then be the integral of x plus 1, which is x squared over 2 plus x, plus the integral of 2 over x minus 1, which is going to give me a 2 ln absolute value x minus 1 plus c. So we immediately can do this problem because of that. Okay. Okay, so summary so far. So if we want to integrate the integral of p of x over q of x dx, and q of x is going to be a product of distinct linear factors, that's an assumption we're making today. then if step 1 is if the degree of P of x is greater than or equal to the degree of Q of x, then we do a long division. That's the first step if the degree of the numerator is too big. Okay, so now let's assume let's now get down to brass tacks with we're now in a situation where if the degree now is smaller. So then what you do there for every linear factor, let's say ax plus b, contributes some number, uppercase A, over ax plus b to the partial fraction decomposition, or partial fraction expansion. So you'll see this work in detail right now. I'm just giving you the, you know, what you're supposed to do. It's a recipe. And now to understand really what the recipe is saying, you have to do some examples. You have to work it out yourself. So let me do an example. So I'm going to do a simple example, 1 over x cubed minus x. Now this is not written as a product of linear factors, so I will then have to factor it. Now that's the hard part sometimes. You have to know how to factor something. If it's a cubic or higher, you might not be able to do that so easily. But in any case, this one's easy enough. It's x times x squared minus 1, which is 1 over x times x minus 1 times x plus 1. So these are a product of 3 distinct linear factors: a linear factor of x, a linear factor of x minus 1, and a linear factor of x plus 1. So the idea is that we would expect that 1 over x cubed minus x should be a over x plus b over x minus 1 plus c over x plus 1, 3 different constants that we have to determine. So now the next step is to multiply by the big denominator on the left. The equation. So if you do that, you get 1 is equal to a. Now, that denominator is factored as x times x minus 1 times x plus 1. So if you take a over x and multiply it by the denominator, what's left over is x minus 1 times x plus 1. And similarly, b becomes x times x plus 1, and c over x plus 1 becomes c times x minus 1. So now you can do either the first method or the second method, meaning you could either expand the right-hand side and then equate the coefficients of the polynomials on left and right, or you can do the test values. I'm going to do test values. Okay, so and the test values which seem to be the best are x equals 0, x equals 1, and x equals minus 1, because things vanish when you put those 3 values in. So if x equals 0, you get the equation 1 equals, okay, so negative 1, so negative a plus 0 plus 0, so a equals minus 1. If x equals 1, you get 1 equals, okay, so the first term vanishes when x equals 1, and the last term vanishes, and you're left with 2b. So that says that b equals 1/2. And if x equals minus 1, you get the equation 1 equals c times minus 1 times minus 2, which tells me that 2c is 1, so c is also 1/2. Okay, so what do we get then? we get that the partial, let me go to a new slide to write down the answer. So we've concluded that 1 over x cubed minus x is 1 over x plus a half over x minus 1 plus a half over x plus 1. So we can integrate, if we wanted to integrate dx over x cubed minus x, that would be the integral of dx over x plus the integral, let's bring the 1/2 out, dx over x minus 1 plus 1/2 the integral of dx over x plus 1. And that's ln absolute value of x plus 1/2 ln absolute value of x minus 1 plus 1/2 ln absolute value of x plus 1 plus c. Okay, so that is the solution to this problem if we wanted to integrate that expression. Okay. So I'm going to do one more example today of this type of partial fraction expansion in the a distinct linear factor case in the denominator. I'm going to do the following example, which goes like this: x squared over x squared plus x minus 6. Okay, so now the numerator has the same degree as the denominator, so you're going to have to do a long division first. Okay, so we're going to let x squared plus x minus 6 go into x squared and see what we get. So we get x squared goes in once, x squared plus x minus 6. Subtract, you're going to get minus x plus 6 as the remainder. And that tells me that this expression is given by 1 plus negative x plus 6 over x squared plus x plus 6. So that's like step 1. You have to write it that way. Now the numerator in the second term on the right side of the equation has degree strictly less than the denominator. And you always have to arrange that so that it happens. Okay, so now so that was step 1. Step 2 is to then figure out the partial fraction expansion of negative x plus 6. Now, the denominator does factor. There's a minus sign that I should have put here. It's a minus 6. It's x minus 3, or is it x plus 3? X plus 3 times x minus 2. Okay, so now we would like to figure out the partial fraction expansion of that. So that's going to be a over x plus 3 plus b over x minus 2. Okay, and then we multiply both sides by the denominator on the left side, so we get negative x plus 6 equals a times x minus 2 plus b times x plus 3. Okay, now in solving this, I'm going to use test values. So test values will be x equals 2 and x equals minus 3. These seem to be the best values to use. So what happens to the left side when you plug in x equals 2? You're going to get 4 equals 5b. So b is equal to 4/5. And if x equals minus 3, you get 9 on the left side is equal to, it looks like to me, minus 5, minus 5a. So that means that a is equal to minus 9/5. Okay, so what does that tell us? That tells us if we wanted to integrate x squared dx over x squared plus x plus minus 6, that would be the same thing. Let me make some space here as the integral of 1 dx plus the integral of a over x plus 3, but a is negative 9/5 over x plus 3 dx. And then there would be another term of the form 4/5 dx over x minus 2. And then we can solve this problem. I'll write the answer down. It's going to be given by the integral of 1 dx is x. The second integral gives me a minus 9/5 ln absolute value x plus 3. And the third integral gives me a 4/5 ln absolute value x minus 2 plus c. So that's the final answer to this example, and this is also the end of today's lecture. Next time we do more complicated cases.